then you can use. Let me try PV equals NRP, so PSI 14.7 PSI 1. Yeah. 86.7 atmosphere. 86.7 liters equals 2.0826 times 28.
Yeah, right. So today we're going to start on chapter 9, thermodynamics. But start class some of those concepts that we talked about in the gases section. And so here we have an example. A pressure gauge on a helium tank shows a pressure of 1275 psi at 25 degrees Celsius. If the cylinder has a volume of 10 liters, how many grams of helium does the cylinder contain? And here I've made a nice little note. Assume an ideal gas. Because on an exam, we're going to be going to make sure that you know that assume is an ideal gas. And so what's my first step that I need to do? Convert to Kelvin. Yeah, I need to deal with my unit conversion. 25 degrees Celsius. We can add 273 Kelvin to it. So I should end up with 298 Kelvin. Okay? What else do I need to convert? PSI. I need to convert my PSI. 1275 PSI. Do I need this value here? That millimeters of mercury? No. Ignore that. Sometimes you're given extra information in a problem that you can just set aside. You can ignore. That helps just cross it out. So I need to convert. Here I have that 1 atmosphere equals 14.7 psi. Okay? And so I should end up with 86.7 atmospheres. Is this an ideal gas? No, really it's not. This is a real gas. Because that pressure is greater than 10 atmospheres. So I expect that my molecules are going to be interacting, but in this case, I've been told, assume that this is an ideal gas. And I've given some options, and so I know probably they're spread out enough that if I assumed that it was an ideal gas, I would still approach the correct answer there. Then I can remember my PV equals NRP equation. Okay? And I can plug in those values. 86.7 atmospheres, 10 liters. Do I know my number of moles? No, that's what I'm trying to solve for. Times my gas constant, and I can look back at that table of gas constants, or look at my extra data sheet on my exam and say, okay, I know that that is going to be that value. And my 298 Kelvin. Then I solve for my number of moles. Would be 35.5 moles of helium. Is that what everyone was able to get to? Okay? So remember your unit conversions on these. Is that my final answer? No. What's my final step? I need to convert to grams. I look at my periodic table and say there are 4 grams of helium for every 1 mole of helium. So I should end up with about 142 grams of helium. Okay, any questions? So remember that ideal gas law. Remember how we apply it. And in this case, we were told, assume that it's an ideal gas. Another big indicator is if that extra data sheet does not include the van der Waals equation, you probably won't be applying it. So if your extra data sheet doesn't have the van der Waals equation, always assume an ideal gas. Okay? Any questions? Or if you're not given the correction factors. I did not give you all those correction factors. If you remember, see if I can quickly pull this up. If you remember from the last lecture, computer. Completely frozen. It's going to make lecture really fun today. Okay. So my computer is not working right now. Oh, is it gonna? Okay. No, it's not. Okay, well, I am dealing with my computer. Here are a couple example problems from active data. And I am going to get my computer working. So feel free to
I thought reading contest.
Oh yeah, for PopCon? Is that tomorrow or today?
It's both days. Popcorn.
I think there's a Hot Wings contest that's today.
Oh
And
god,
there's
I
the
died.
oh wow, your popcorn thing? Fancy.
Take a break. Not because like
We started, but promising to still not work. So we're going to make this happen today. It's going to be a little different.
Thermodynamics. Oh boy. Yeah, it is what it is.
It looks like Microsoft Office is just having issues right now, so if it crashes again, then we'll just move to the board. But hopefully that's helpful to see a couple more of our exam questions too. Don't forget your attendance code. Okay, so we are going to continue on chapter 9, thermodynamics. So don't forget that your chapter 8 homework is due on Sunday at 8 p.m. So remember, it's set to Sunday. So you have a couple extra days to work through that. And then the thermodynamics homework is due next Friday. Okay, so we're back onto that Friday sequence. So just pay attention to those deadlines. And then don't forget that Friday, the 21st, we have our exam 3. Okay, so Friday the 21st. And I'm going to put up a poll maybe later in class or on Monday about exam 3. In the past, I have either done, I've done a couple different things. Done once closed book, once where a note sheet was allowed, and another time we just let it be everyone can work together. Closed book, but everyone can work together. And it is a bit of chaos in here when that happens. So I'll put up a poll probably later in class where you guys can weigh in on what you would like. So we try to make exam 3 a little bit more collaborative or a little bit more fun.
Oh boy. So does it mean it's harder?
Oh, what if you're separated into the other rooms?
Well, no, I could go in here if it was collaborative. I just.
Wonderful.
Final is a week or a month, a month and 2 days away, right? It's December 9th. On the final exam, this is a national standardized exam, the American Chemical Society exam. There are national norms for it, so I calculate what percentile of the nation for general chemistry you fall in. If anyone scores above the 80th percentile, so long as you've been to your labs, you automatically get an A in the course. So, score above the 80th percentile. It's tricky. It's tricky. Folks in the back, the two TAs, They know about the ACS exam. They know that it's a tricky exam. So if you score in the 80th percentile, that means that you are performing in that top 20% of chemistry students nationwide. Then you get an A in the course. Okay. So hopefully that is motivation for study, especially for those who are maybe on that, especially on the cusp of like a B and C. I see those people are the ones that put in that most effort to try to bump themselves up. And regardless of where you stand in the class, except you have to be able to pass the lab. Okay, you have to miss less than 4 labs. If you miss 4 labs, it's just sort of out of luck. Fail the course automatically. But anyone else, automatic A. Okay, so be studying for that final. That's your chance. Okay. Any questions? Yes.
Do you have like any, are you gonna post recommended topics to focus on for the final exam?
Yeah, so we will spend the whole week after the exam going through the final exam topics and practice questions. And I will post, just like for the other exams, I'll post a PowerPoint. Yeah.
How many?
Is it 70? 70. Okay, I was going to say 70 or 75, and now I'm blamed it for like not come prepared. You have 2 hours to do that exam. And it's all multiple choice. Okay. So find your study group. Okay. So before we get too sidetracked, so that we are still, yes.
I also want to real quick say there are lab topics on the exam too. So make
There
sure
are
you study your lab.
Yeah. There's a few lab topics. It's not like overly heavy on lab topics, but there's a few. There's a few. Things like measurements, how you figure out uncertain digits, too. That sort of stuff. You see class here.
Yeah.
Okay. Okay, so let's jump into thermodynamics though. Okay? Now we're about a quarter of the class is gone at this point because tech errors and excitement about upcoming exams. So in chapter 9, we are talking about energy. Thermodynamics, it's all about energy. And here we're really thinking about 2 broad categories of energy. And those units are going to be in joules. We've seen that before, right? You guys are all familiar with joules. We talked about that in chapter 3 when we talked about wavelengths and the energies of photons. And now we're going to talk about these 2 categories. Kinetic energy, that's the energy associated with motion. Okay, here I have a lot of kinetic energy. I'm in motion right now. Potential energy is associated with the position or configuration. It's your stored energy. IVA, up at the top, has a lot of potential energy. There could be a lot of energy down the stairs. Please don't push it down the stairs though. We love IVA. And then work is the process of transferring energy from one place to another. So, as the example of Iva, sorry Iva, I'm just picking on you. Your office hours are this afternoon, by the way. In case anyone's looking to go to office hours. If Iva walked down the stairs, you're putting in some work. Just moving that potential energy, kinetic energy, and from one place to another. We change the form of energy as well. Work has the units of joules. And here you can see that energy movement, we think about a mill, okay? We don't oftentimes think about things too much anymore, but we're taking that kinetic energy and we're moving it. You see that here at the top of the hill, that ball has a lot of potential energy. Once this person pushes it down the hill, that energy is converted into kinetic energy. The energy is motion. There's a lot of forms of energy, types of energy. If you are in engineering or in physics, then you're going to be talking about a lot of types of energy. We are going to be talking too much about all the different types of energy. Okay? So feel free to take a look at the list, but don't worry too much about the types of energy. But a big thing we'll talk about is the conservation of energy. Energy can be converted from one form to another. Conversely, from potential energy to kinetic energy. But it cannot be created or destroyed. The energy of the universe is constant. Okay? So we are never creating energy in this class. So please remember that conservation of energy. So we'll talk about thermodynamics. This is just the study of energy transfer associated with change in a system. Okay? This is our energy accounting. We've done a lot of electron accounting, atom accounting. Now we're energy accounting. You guys are just becoming chemical accountants in this class. And thermochemistry, that subtopic that focuses on heat and chemical reactions. Who has ever used hot hands? Yeah, that's all just thermochemistry right there in your hands. So we'll talk about those types of reactions. And we'll talk about there's the part of the universe which we are studying. If you're working in or maybe you're an atmospheric chemist and you're thinking about the whole atmosphere, that's your system. Or a cell if you're a biologist. The surroundings are going to be the rest of the universe. Now this looks a little bit abstract to think. Okay, if our system is in this classroom, the rest of the entire universe is our surroundings. Here we could say the universe is going to equal our system plus our surroundings. And remember, we're not changing the energy of the universe. So we can change where energy is, whether it's in our system or in our surroundings, but we are not changing that total sum, the energy of the universe. Any questions so far? Okay. So here we can have some different types of systems. We can have open systems. This is your bowl of soup that you're about to eat. This can exchange matter and energy with the surroundings. You do heat, that can exchange heat, or the work can be done on it. This is an open container. So you can see here your cup of soup, where you can have that steam release, that heat can move. Maybe you can put matter in the form of grated cheese or crackers. And you can take matter out with a spoon. Or you can see here in this bottle example, where it's an open bottle. You can take in or put out. Now, material. You also have this exchange. We've all probably felt a cold bottle of water from the refrigerator, or maybe a warm cup of tea, where you can have heat exchange from the walls of the container. In a closed system, you can exchange energy in the form of heat or work with the surroundings, but not mass. So here, when we take our cup of hot soup from our takeout container, it has that lid on it, so we're not putting matter in or taking matter out, but you can still lose heat to your surroundings. And so you can have that transfer of heat. Here you can think about if I put some cold water into my water bottle, then I can feel that it is cold on the outside. I know that there can be some heat exchange. And then there can be an isolated system that does not exchange matter or energy with the surroundings. Oh, someone in here probably has an insulated cup. If you put hot tea in it, you can't feel that it has a different temperature than the surroundings. And so here in this example, if you put your soup into a thermos, you might say that's an isolated system. Here you can see that container. It's been isolated. So we can think about 3 different types of systems. And when we're talking about this, their isolated system, we're going to assume that their containers are perfectly insulated. Do you think that is the case? No. No, we're never going to have a perfectly insulated container. But in this class, sometimes we do have to assume some level of perfection. So if you're told that you have an isolated system, just assume that it's perfectly insulated. Okay. Any questions? So we're going to think about the first law of thermodynamics, the conservation of energy, and we've already talked about that. So if the energy changes, the surroundings must experience an equal and opposite change. Here, change in the energy of the universe equals the change of the energy of the system plus the change of the energy of the surroundings. That should always be 0. So the change in the energy of the system is the opposite of the change of the energy of the surroundings. And since we're only interested in the system, we can drop the subscripts and just do that energy accounting on our system. So we focus on just computing this change of energy for the system. We're not worried about the rest of our surroundings. We're just worried about that system. We just assume that the surroundings will be equal magnitude and opposite in direction, in sign direction. So here, we think about the process of only exchange of heat and work between the system and the surroundings. Here you can see this example where we have some heat added to our system. And you can see that our weight moves. So the heat transfer, which we're going to call heat Q, okay? We're going to say heat transferred to the system is going to be Q. A positive Q, the heat transfers from the surroundings to the system. Okay? So, if you start with a cold bottle of water and it warms up through time, you have that positive heat transfer. Okay? The heat has been transferred from your surroundings into your bottle of water. But you can also say that work can be done on the or by the system. It's going to be W. And a positive work value says that work is done by the surroundings on the system. Okay? And the change in energy of the system is going to be our heat transfer plus our work done by the system. Okay? We're not really going to worry too much about work. So don't worry too much about work unless you're given a work term. Most of what we're going to talk about is heat. The transfer of heat to the system and out of the system. And so we can talk about the flow of heat. Okay? So heat and work are 2 ways energy moves between the system and the surroundings. We've already introduced that change of energy is our heat plus work. Work is the force exerted through a distance. Okay, this is very much a physics thing, not as much a chemistry thing. So we're not going to worry too much about work. But work is a force times distance. Okay? And we're going to talk about the internal energy, the energy of our system as a state function. Okay? The state function